at least 2 classes a week, maybe sometimes 3 classes if we can find the slots. Okay, so I'm starting. Okay, you remember in the last class we went through this discussion of bosonization in a great deal of detail. One of the punchlines of the discussion, of course, was that the free fermion, or 2 copies of the free fermion, 2 copies of the right moving free fermion and 2 copies of left moving free fermion become a scalar field at 1 by square root 2 or square root 2 times the self-dual radius. Okay, that was a statement about a physical theory. However, most of what's going to be important for us will be a statement about chiral algebras. And the statement about chiral algebras didn't care about left moving and right moving. Just a statement that the algebra of 2 fermions, let's say purely left moving, was the algebra of the left moving part of a free boson. And then at the end of the last class, we also applied this to the analysis of the BC system. And we understood that the BC system could be bosonized, and the effective scalar had a linear dilaton term in its stress tensor. Okay, great. Now, now what we're going to do is to see what we can say about the beta gamma system. Okay, so let us remind ourselves what we know about the beta gamma system. So let's put on the board what we know about the beta gamma system. Just so that we get the notation all right. So S was equal to, in Polchinski strange d2z units, d2z divided by 1 by 2 pi. Remember, d2z was 2 times dx1 dx2. Okay, d2z divided by 1 by 2 pi, beta del bar gamma. And as we've gone through, of course, we know that del bar of beta is equal to del bar of gamma is equal to 0. This is the equation of motion from this Lagrangian. And we found that beta z gamma of 0 was the same as minus of gamma of z beta of 0, which was 1 by z. Sorry, minus. So minus beta z gamma of 0, which is same as gamma z beta of 0, is 1 by z. The last thing I'm going to remind you of, it was that the stress tensor was del beta gamma, always normal ordered, minus lambda del of beta gamma. And this theory had a central charge C is equal to 3 into 2 lambda minus 1. The whole thing squared, minus 1, and the weights were h of beta was equal to lambda, this beta was like b, and h of gamma was equal to 1 minus lambda. Okay, so all this is from the last time we studied the beta gamma system. This was just a reminder of these results. Lambda was 3 by 2 for the case of special interest, but yes, and we will often specialize to 3 by 2. But for the discussion of bosonization, we will not need that. We will do it for arbitrary lambda. Okay. Okay. So now the first thing we're going to try to work this out in parallel with what we saw for the BC system. Okay. So for the BC system, one of the things that we that was interesting was that if you take the operator BC at z, and we took the operator BC at 0, okay, then what was this operator? So this operator, well, what is the OP of this? I'm going to work out the OP. Okay, the most singular term in the OP is BC with BC. So B goes through here, through this C, so that's 1 minus sign, then goes through this B, so that's another minus sign, then it hits the C, so we get a 1 by Z. And then we have a CB, which is another 1 by Z. So this went like 1 by Z. Now, you might say, well, what about, okay, let's look at the subsequent terms in this OP. Okay, so let's take just one of them contracting.
Yes.
Let's say this BC going and hitting that. So that will give us plus C of Z B of 0 over Z plus B of Z C of 0 over Z.
The most singleton conditions.
Exactly. So this looks like there are 1 by Z pieces here, except they're not, right? Because
C0 B0 plus B0 C0.
exactly. We can Taylor expand both of these. The leading term is C0 B0 plus B0 C0, which is 0. Okay, so the coefficient of 1 by Z was just 0. Okay, and so actually the only non-singularity, the only singular term in this was plus non-sing. And this matched very nicely with the identification under bosonization of this BC with del phi. Okay, now I can't remember the i's in that identification. We'll put the i's. Did we call it H last time?
Yeah, it was
I del H. And
it's the U1 current.
what?
It's just the U1 current.
The U1 current. I del H. And our H was normalized how? Del H. H of Z, H of 0. Was that minus log Z? Or was it plus log Z? Well, let me look.
No, it's minus log Z.
H of Z. Very nice. Was minus log Z. Okay, fine. So then let's now compare that. Let's now check that we get the same 1 by Z squared from this I del H. Okay, so we have I del H, so that's minus. Okay, then we have del of H of Z with del of H of 0. Okay, up to a minus sign. Let's check the minus sign. So it's right. Let's see. So that's I del 1 del 2 of so plus log of Z12. Okay, so let's take the del 2 derivative that gives minus. Yeah, it works. Right? Oh, no.
Yeah, because then you have the 1 over Z, which
Yeah, it works. So that's equal to 1 by Z12 square. If we take the del 1 derivative first, the first one has no minus, and then the second one has 2 minuses. Because derivative of 1 by Z is a minus, and also we are doing the other derivative. Okay, so this worked beautifully. There were two ways of getting the same singularity, and this was, the heart of bosonization. The heart of bosonization was that the current, the fermion current, which is BC, phasing of B and antiphasing of C, was translations in the boson. Okay. So now that this worked so nicely, we are going to need, and you'll see why we're going to need this in a minute, we're going to need an analogous representation for beta gamma. The reason is going to be that, the vertex operators for the beta gamma system that we will need to insert into our string world sheet will be vertex operators that have a simple form in bosonized language, whatever that means, but have no simple form in beta gamma, just like the Ramon state operator, the Ramon state ground state, for instance, had no simple expression in terms of fermions, but had a very simple expression, namely e to the power plus minus phi by 2, in terms of the bosons. Okay, so for that reason, we're going to need this this new representation, because we're going to need, because as you will see, the things that we will need to insert on the string world sheet involve these funny powers of will be things that have simple expressions in bosonized language. Okay, so for that reason, we want an alternate representation of the beta gamma system. Yes.
just sort of like a naming question.
Yes. Why is it bosonization? Because it's already. It shouldn't be called bosonization. It should be called simplification, re-algebraification, whatever you call it. Yeah. Okay. Yeah. In fact, it's going to be a fermionization because we will re-express it in terms of fermionic. Bosons and fermions. It's just a name, okay? It's just a name. Okay. The point is that we want to be able to express operators for which there is no simple algebraic expression. We will get a larger algebra. A larger. Let's look at the fermions. Okay. Let's look at the fermions and the bosons. The fermions were very natural for expressing e to the power ih, or e to the power 2ih, or e to the power 3ih. But the bosons could very beautifully express e to the power I alpha h. Okay, so the fermionic algebra was then embedded inside a larger bosonic algebra. That's the kind of thing we're trying. To embed the natural algebra of these beta gamma inside some larger system. Because we will need that larger system for vertex operators in the ground states of physical interest. You will see how that works. Okay, so that's what we're after. We're interested in embedding the algebra of the beta gamma system inside some larger algebra, and we will see immediately, probably in this lecture, why we need that. Okay, that's the only thing we're trying to do. What?
One can also, in principle, work purely with fermions, but it will be difficult.
It will, yes, but you see, we're going to have to then define these operators. Suppose we wanted to define the operator e to the power I alpha h in terms of the fermions. The way we would define it is this. We would, suppose we knew the bosonic representation. Then we would take the OPE of e to the power I alpha h with e to the power h. Let's do that as an exercise. So suppose we take e to the power I alpha h with e to the power of z with e to the power ih of 0. Okay? Now, this thing, let's look at its singularity of the OP. So this thing is going to be e to the power, now I minus, then the 2-point function of the h's. Okay? The 2-point function of the h's, so that's minus alpha and then minus a plus log z times normal ordered e to the power I alpha h e to the power I h 0 z 0. Okay? Now this is some strange beast, right? Because this is z to the power alpha times this. Now, once we have realized that it is possible to define a consistent algebra with all these e to the power h's, what we would do in the fermionic, now this of course is just psi. Okay? So what we would do is to try to define an O alpha with the properties that O alpha of z, okay, times psi of 0 goes like z to the power alpha times single valued, and O alpha of z times psi bar of 0. Okay, it's the other psi, okay, it's nothing to do with anti-holomorphic, remember there are two psis. Goes like z to the power minus alpha. And actually, this plus holomorphicity is, and one or two other small assumptions, are completely enough to fix the correlation functions of this O alpha. So that's the way in which we can in principle work. Okay, O alpha then will just be defined by these relations. That the single valued nature, the lack of single valuedness of O alpha with respect to psi is given by these. And actually, the people who first worked out such operators, I'm not sure in this context, but in similar contexts, orbifolds, so on, these papers by Schenker and Martinek and Friedan, this is how they worked. They actually worked out these twist operators.
If you had one of them, then probably you have to work like that.
Yeah, exactly. Exactly. Well, of course, if you had one of them, you wouldn't be able to. In a very similar context, let's say you wanted something like an orbifold, the twist operator for an orbifold.
Z2 orbifold.
Z2 orbifold. Okay. The twist operator, the operator that's dual to the twisted sector. Okay. We know from on general grounds what its operator product expansion with the other operators has to be, and in that case, sometimes there's no other representation.
I have one.
Please go on.
How is this, you have written down the partition function of psi theory by looking at bosonization picture.
Yes.
And that in terms of torus it had all the combination. modular invariant combination, and how would that be different if you had considered a G2 orbifold for the fermion?
Z2 orbifold for the fermion. Now I normally Z2 orbifold bosons.
Yeah, I know. I'm asking this because the boundary conditions you have considered periodic, antiperiodic on the space.
Yes.
And for each one of them, you have considered time to be periodic and antiperiodic.
Yes.
Which is, if you are doing an orbifold by the Z2 symmetry of the Hilbert space.
And what is the orbifold you're looking at?
I'm trying to think about this answer. Can it be thought about as Z2 orbifold for the fermions?
Oh, that's what your question is. You're asking, is the addition of the Ramond sector effectively like a Z2 orbifold?
Yes, that is my question. I don't know the answer.
Because it's similar, because you've got
You have summed about
all these things. So let's say that you orbifold by sort of psi goes to minus psi.
Yes. And this is a commuting action.
Yeah, it looks very similar to what you would get if you did that. So it sounds right. I haven't thought it through carefully, but it sounds, you would get the same. These are the words you would attach to that partition function, right? In fact, there's only a matter of signs. The signs are all plus, so it looks okay. Probably right. Probably the words are appropriate to say that if you took a fermionic theory and orbifolded by psi goes to minus psi, this is what you would get. That sounds right. Certainly it's a symmetry of the action, because everything's quadratic. Sounds reasonable. Sounds like good words to put to it. I'll let you know if I can think of any subtleties. Okay, let's keep going, please.
Last time when we worked out the similar thing for the BC system,
Yes.
we said, in other words, if this is my stress tensor, and suppose I wanted to represent beta gamma with something of this form,
Yes.
I know what h of beta and h of gamma have to be, and we sort of worked this out already to be BC. In other words, if you want to have two operators, they're going to be of the form e to the I alpha h, and I want them to have that stress tensor and have those scaling dimensions, and the answer is the BC system, isn't it?
Yes. So you might wonder, so you might be saying one of two things. A, you might be saying this cannot work. B, you might be saying it has to work. Which one are you saying?
It has to work, but it's going to end up.
Okay, it has to work. Let's check. That's exactly what I'm going to do. Okay. You know, I was once giving a talk and somebody got up and said, look, what you're saying is either wrong or trivial. I said, well, you have to make up your mind. Okay. Okay, so I'm clearing all this. This was a reminder for the BC system. Now we can try to do it for the beta gamma system. We'll keep this on the board till we finish our work with the beta gamma system, so we don't have to keep looking up formulas. Okay, so we're going to take a cue from Yankee. Okay? Theta, what is theta? No. The d2z, d2 theta was in the formalism that led to getting this beta gamma. Now we've integrated out the thetas. Okay, so this is just the pure system. That formalism was useful in trying to understand what our theory must be. Once we've got our theory, we will often not work in superspace. Sometimes we will, sometimes we won't. Okay, great. So, now the question we're going to ask is this. What about if we try to do something similar? So, now I'm going to use the notation that people normally use for this thing, for this beta gamma system, and in that language, okay, let's suppose that that what we called h last time is now called phi. Okay, that's the usual. And we'll once again work with a scalar phi of z, phi of 0 is equal to minus log z. Okay, standard scalar. Okay. Now the first thing we're going to do is to start with beta gamma of z times beta gamma of 0. This is what we did 2 minutes ago for the BC system, and let's see what we get. Now, one thing we do, firstly there are no inconvenient signs in taking beta through gamma because they're all bosonic. But we get beta with gamma and we get gamma with beta. First difference, Yankee. First difference is that while beta with gamma with beta is 1 by z, beta with gamma is minus 1 by z. So already we see our first difference with the BC system. Where we had 1 by z squared, now we have minus 1 by z squared. Okay, that's going to be the key thing, that various signs will behave funny. Okay, fine. Okay, so now how could we try to do some sort of bosonization? Well, let's also look at beta gamma of z with beta of 0 and see what we get. Okay, so let's look at beta gamma of z with beta of 0. So we get gamma times beta, so that's equal to beta by z. On the other hand, if we look at beta gamma of z with gamma of 0, okay, we get minus gamma of 0 by z. I'm only writing the singular parts. Is this clear? Okay. Now, suppose we want to mimic our previous bosonization. It feels like what we want to do is to set beta gamma is equal to del phi rather than I del phi. So that if we take beta gamma with beta gamma, instead of picking up 1 by z squared, we will pick up minus 1 by z squared because same calculation as before. The I squared will not be there. Okay. Now, suppose we want to try to get these OPs right. What should we do? Well, let's try. Suppose beta gamma is del phi, so we've got del phi of z. And now we want beta to be e to the power beta by z. Let's try something. Something like this might work. Let's try. We want some operator that has charge 1 under translations up to some i's. Yeah, so this is, this doesn't work, we'll change some signs. Maybe put some i's. Let's see if this works. Okay, so now we do what we always do. So I'm going to try to work out this OP. So this is del phi of z. This is sum over n phi to the power n by n factorial. Okay, there were n choices, blah, 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 the usual story. And then we get phi with phi. That was minus 1 by minus log z becomes minus 1 by z. Okay, so that becomes minus and then 1 by z times e to the power phi. Sorry, don't worry. So this was the other one. Let's check. Yes. So we'll try this. Now this will become a plus. Right? Because we will. There was a minus 1 to the power n. And then that becomes minus 1 to the power n times phi to the power n minus 1. So you pull out a minus 1. Okay. Minus phi to the power n. So, and this will become plus. Is this clear? Okay. On the other hand, what about beta gamma with gamma? We want this one. Now this one worked with the other one. Okay. So our first guess might be beta is equal to, our first guess might be beta gamma should be equal to del phi. Beta should be equal to e to the power phi minus phi, and gamma should be like e to the power minus plus phi. This is what you might think. This would be a very close cousin of the BC system, but it doesn't quite work.
Because beta gamma itself, if we take this to the fundamental, then
Exactly.
the first line wouldn't work.
Exactly, exactly. Let's check. The problem is that the OP between beta and gamma doesn't work.
Yeah, beta gamma will not be beta gamma given above.
What?
If you take definition of beta gamma below,
You're saying we'll get a minus sign off. Let's check. Let's. Oh yeah, you say you will get just one, but remove the singularity. Let's check what we get if we do that. Okay, let's take beta with gamma and normal order. Okay, so beta with gamma, beta of z with gamma of 0, and then normal order, and then take the limit, z goes to 0. Suppose we get suppose we use e to the power minus phi, so we will get e to the power now z to the power plus 1, right?
Plus 1.
Yeah, right. This is, you're right, it doesn't work. Because you get z times e to the power phi of z minus phi of z plus phi of 0. And then there's an identity piece and a del phi piece.
Yes.
Okay? Previously in the BC system, if you did the same algebra, that the z would become 1 by z.
yes,
That 1 by z piece,
hit the identity.
then you have e to the power whatever.
Yeah.
That e to the power whatever is 1 plus del phi,
Times.
1 plus z times del phi.
Yes.
The 1 is removed by normal ordering, because 1 by z.
One got removed.
By normal ordering, and what was left was the del phi. Okay? It's basically the signs that are killing us. This z, instead of being a 1 by z, was a z. That was what was not working. So you're right, it doesn't work. And another completely related thing that doesn't work is if we look at the operator product expansion between beta and gamma, that doesn't work. Let's check that. Suppose we take beta of z with beta of 0. Okay? What is this supposed to be? This is supposed to be order. This is supposed to be, it has no singularity. So it's supposed to start with order 1, beta of 0 squared. Okay, let's see what it actually starts with. Let's see what it starts with if this guess was right. Remember?
Yeah, this will start with 1 over z.
1 by d.
Yeah, exactly. So, exactly. So, if we write e to the power minus phi of z, e to the power phi of 0, minus phi of 0, this goes, minus minus cancel, there's a minus from there, so it's 1 by z. So it doesn't, not right. Also, similarly, gamma gamma will be 1 over z. And as bad, beta gamma will be z. When it should have been 1 over z. It's just a matter of these signs, right? They're just not working. So something's wrong. So either we've got completely the wrong idea or we need a fix. Okay? What? Okay, we're going to try something. So what we're going to do.
Signs, this is what I'm saying. Maybe a twist operator when it passes through them.
Okay, something a little more sophisticated. I don't know what you mean by twist operator, but something quite nice works. Suppose, so this doesn't work. Okay. This doesn't work, but I'm now going to tell you what does work. suppose you let beta be equal to e to the power minus 5. See, this e to the power minus 5 was nice because it had the right charge under the current. We're going to try for a bosonization under which beta gamma really does become del phi. Okay, there is a phi in the problem, and beta gamma does become del phi. That's what we're going to aim for. So the phi dependence is good because it has the right charges. Okay, what we're going to do is dress it up with another conformal field theory to make all the bad things that weren't working now to make them work. Okay, so we're going to try, let's try beta gamma is equal to e to the power minus phi del zeta. Beta, sorry, is this, and gamma is equal to e to the power phi, and what does Polchinski call it? Eta? Let's say eta. This is another very good point. Dimension.
Now you've got the right dimension from.
Well, we don't yet know what the linear dilaton term for phi was. It's too quick to conclude dimension for e to the power phi was half.
If you say that there is a dilaton term,
Yes, and remember for the BC system we needed that. So this objection would have killed even the bosonization for BC, so we don't want to. Okay, so we won't compare dimensions too fast because those can be mixed around by adding a linear dilaton term. Okay, first we'll get the algebra right, then we'll worry about dimensions. Okay, fine. So let's go. So we've got this, and now I'm going to propose. Of course, I haven't told you anything unless I've told you what eta and zeta are.
supersymmetric version of the bosonization. We got all this beta gamma from the algebraic.
Yeah, is there a supersymmetric version of bosonization? There probably is. Actually, I've never tried to work it out that way. Yeah, you will see that the final answer looks very far from some superfield on BC. See, there probably is though. I'm not sure. It's like this. Suppose you've got a supersymmetric. Suppose we took the world sheet theory of the string. There's a boson and a fermion. And there's a very nice superspace realization of that net system. Now you bosonize the fermion. Now you've got a theory of two bosons. Or a bunch of bosons, and it'll be hard to put that in superspace. You might be able to manage eventually, but there'll be nothing natural about it. So it's this bosonization often mauls that structure. So I'm not sure. I've never seen it done, and I'm not completely sure that something nice exists. Okay, but let's keep going. What is this zeta eta structure? Well, I'm going to assume that this is what works. We'll check it works. Eta and zeta behave like a BC system.
Essentially, two copies of the BC system.
One copy of the BC
One
system
copy, okay.
and a scalar. Now, of course, if you want to call the scalar another copy of the all of these, yeah, okay. Yeah, let's forget about that. Yeah. Okay, and eta of z, eta of 0, which goes like zeta of z, zeta of 0 goes like z. So eta and zeta are anti-commuting variables, okay? Okay, eta and zeta are anti-commuting variables.
But then beta and gamma also become anti-commuting.
Now this is a hard one. When I said psi was e to the power ih, psi is anti-commuting.
Okay, right. Yeah, it's a structure of the algebra.
Yeah, it's actually a good question. This e to the power, when you split up a boson into left moving and right moving, it can happen that the left moving and right moving parts anti-commute, even though the boson doesn't. You can see that from the algebra. See, e to the power ih of z times e to the power ih of 0 was minus the minus of z times something. And that z tells you that if you take You flip them, you pick up a minus sign. You know, so it's hard to eyeball it
I see.
and to see about the commutation relations. If the algebra works out, then we know that the commutation relations are also working out. Okay? Actually, there's an interesting Hilbert space point of view on this. The condensed matter people love this. They call it the Jordan-Wigner transform. And they define these things carefully in Hilbert space with these lines that go off to infinity. And they make a big deal of the fact that you can take a boson and make it anti-commuting. And maybe we'll talk about that, but not immediately. It will take us too far out. Okay? So from the point of view of Hilbert space, there's, if you think of it not in terms of path integrals and the operator product expansion, but Hilbert space, there's more of a question, and there's a beautiful answer to it actually. Okay, but which the condensed matter people won't know any of this, but they'll all know the Jordan. If you go to your condensed matter friends and you ask them about Jordan-Wigner transform, they'll draw a lattice, they'll draw. Everyone knows about this. Okay, so it's a beautiful story, but we won't get into it now.
When you say that these act like the BC system, you mean that we're also going to put contributions to the stress tensor for like the whole...
The whole shebang.
Okay.
It's a product of two conformal field theories, a conformal field theory for phi and a conformal field theory for zeta eta. And I haven't told you what the linear dilaton is for phi, and I haven't told you what the improvement term, what the effective lambda is for eta zeta. We'll get to that. I have to tell you.
It's not going to be the same as what we would
It
normally
has
take.
to be sort of, because otherwise the
Dimensions don't work.
Wrong now.
Yes, so we'll fix it up to make it work. But first let's see the algebra. Okay, until the algebra works, there's no point looking at dimensions, because dimensions are an issue of the stress tensor. Okay, which on flat space doesn't affect correlation functions. But at least the algebra should work, then we can worry about dimensions. Okay.
And in all these cases, the equality actually means an equivalence. I mean, not that this is exactly an operated equality.
Well, if you compute correlations of one side,
Yeah.
you'll get the same answer as correlators of the other side.
Yeah.
Whatever you want to call that. Okay, I call it equality, but okay. That if you want to compute one set of correlation functions, it's equivalent to doing that calculation. That's all we care about.
Yeah.
Okay, all of this is a trick to efficiently calculate correlation functions of operators that we're interested in. That's all that it is. But it's a very useful trick. Okay, great. So now let's check all the offending parts of the algebra and see if they now work. Let's look at beta with itself. Okay, last time what we got was minus, and we got 1 by z. Last time what we got was 1 by z. Is that's right? We got 1 by z, and then now, so that's what we get from here. But then we get also del zeta of z, del zeta of 0.
Yeah.
Now, this is a fermionic field. So if we set this to 0, it's 0. So the first term that occurs is in Taylor expansion. And therefore it's order 1. That's exactly what we expect from beta with beta. Remember, beta was bosonic. So we expect beta with beta to be order 1. Okay, great. So that fixes up beta with beta. Exactly the same argument fixes up gamma with gamma, because we get eta of z, eta of 0. Again, if we just set z equals 0, that would be 0. We have to Taylor expand, so it will kill the 1 by z. Now, so let's now check beta with gamma. Okay, so we have, last time what did we get? We got a z. Okay, but now we have del zeta of z with eta of 0. Contract this, that gives us a 1 over z square. Okay, now we get 1 over z and then actually a minus 1 over z square.
Do the beta gammas and the eta zetas contract at all? Do they?
No, completely decoupled conformal field theories. Sorry, what were we saying? No. Beta gamma are expressed in terms of these. So we'll never use language where we have both beta gamma and this. The phi's and these are completely decoupled.
Okay, I guess that's where I should ask the phi and
The phi and these are completely decoupled. Okay? Great. So this will become minus 1 by z plus regular. Is this clear? Okay. Now we got minus 1 by z when we did
Yeah.
beta gamma,
Yeah, that's what it is.
which is perfect. On the other hand, when we do gamma of z, beta of 0, now the del is on the other side,
Yeah, so it will hit z2, del of z2.
and therefore it will be 1 by z plus regular. Okay. And finally, let's look at Indranil's objection. Is beta gamma actually equal to del phi or not? So let's work that out. So last time we got z times normal ordered e to the power minus phi of z plus phi of 0, right? But now let's look at the part that came from beta gamma. So we also need del zeta of z, eta of 0. We take the OP of that. Okay, we take the OP of that, and we will get a term which is z times normal ordered stuff, e to the power minus phi of z plus phi of 0. Okay, and we will get 1 by, this was z, so minus 1 by. Exactly. This basically changes the z to 1 by z square with a minus sign.
Minus sign works out
Because of that minus thing. Now when we Taylor expand this, this becomes del phi. We throw away the 1 by z because of the normal ordering. Some of you might be worried, well, what about the Taylor expansion of this guy? But you see, that's in the regular part. Because the only reason there was an irregular piece at all, the only reason, that's in the part that's z and higher. Because there's an explicit z here. So all of that comes at higher order. The part that is 1, that survives after you remove the Taylor expansion. Okay, the part that will survive, you remove do the normal ordering and take the operators together, was just the del phi. So you see how beautifully it works? Is this clear? Okay. So now we're happy. The algebra works out absolutely beautifully. Now that the algebra is working, we have to answer more detailed questions. So the first question that we're interested in is what are the weights, what is the slope of the linear dilaton for phi, and what are the weights of the beta gamma system. Okay, now, so to answer that, we're going to try to compare with other OPs that everything should work out. So we'll try to make everything work out and see how it goes. So the first thing we do is this. Everything involving weights is now a question about stress tensors. So we have to bring the stress tensor into the game somehow. Okay.
Fundamental about putting the derivative in beta.
Yeah, well, it wouldn't work without putting the derivative in eta. I don't know, but fundamental.
Why I'm asking that if instead of putting the derivative in beta, can you put it in gamma?
Instead of putting the derivative in beta, can you put it in gamma? It might be that if you do that and then flip
Flip a sign.
Signs like I and
flip the linear dilaton sign,
then it will know.
it might be. I think, and then maybe change the weight of the, you'll have to change, I think we might be able to change all signs in some way. Because you can take this beta, gamma, this zeta, eta, and bosonize that. And then if you just flip all signs, of signs of all bosons, it might work. So that will mess these around, maybe. I'm okay, I'm not sure. I think it should work. I think it should work. Though, of course, these are not. At the level of algebra, no, wait, let's be slow. At the level of algebra, it would not work if this was here and this was there.
Signs will go wrong. Right?
Signs will go wrong in beta gamma and gamma beta.
Can you fix it with
Yeah. So,
I am asking because should I remember that the derivative should be in beta? Sorry for this.
yeah. Okay, if you just flipped, it won't work.
Signs will obviously, all signs will go with a minus sign.
You might then want to flip these signs.
Then also it will not work.
Yeah.
Because the relative sign is.
The relative sign is all that's important. You're right. You might want to fix it by, as Indranil suggested, putting eyes outside here. Okay, I don't know. It's not clear, not immediately clear to me that it will work. Yeah, because beta and gamma are actually different. Right? Beta with gamma is 1 by z. Gamma with beta, it's not like BC where they were on equal footing. Right? From the point of view of the action, either the action is beta del bar gamma or minus gamma del bar beta.
Yes, beta, gamma and B and C are different objects. So the one was in indices wise.
Right. And B and C at the level of action, at the level of algebra, were on completely equal footing. They're different weights. But level of algebra, there was no difference between them. But even at the level of algebra, beta and gamma are not the same. Okay, so there's, even at the level of algebra, before getting into weights, they are different and so may not work. Yeah. Okay. So let's go. Now what we want to do is to bring the stress tensor into the game. So we want to use some facts that we know about the stress tensor. So the first thing we're going to do is to look at the OP between the stress tensor and what's basically the fundamental object in bosonization, namely the current. Okay? So let's look at what T of beta gamma, the stress tensor of the beta gamma system, at Z, and beta gamma at 0 is. And we're going to work this out from first principles, from the beta gamma language, and then try to get matching with what it should be from this side. So the point here is that beta gamma mapped entirely to phi. So we want to do a calculation which doesn't mix up phi and the eta zeta. Okay, so this will give us information of what the stress tensor in terms of phi looks like. Is this clear? Once we compute it. Okay, so let's compute it. So T of beta gamma we have written here. So that's del beta gamma minus lambda.
You are saying this part of the stress tensor is only the phi part.
Exactly. So there are two decoupled conformal field theories.
So it just sees the stress tensor.
Stress tensor of the phi part, exactly. So we'll be able to figure out basically the slope of the linear dilaton from this computation. Because we'll get information on the phi part of the stress tensor.
Yes.
Once we know that, we'll know the dimension of e to the power phi.
Yes.
So then we'll be able to figure out the effective lambda value of zeta, and then we'll do a consistency check. We'll check that the central charge is working out right.
Are we going to end up having two dilaton terms, one for the phi theory and one for whatever the bosonized?
Yes,
so
we'll have.
Now we're just figuring out the dilaton term for the phi theory.
For the phi theory. Yes. And then the bosonized eta gamma, though we will never really bosonize the eta gamma, eta zeta. We'll never have a use for that. As you will see, the vertex operators that enter in the string world sheet sometimes have simple factors of this eta and zeta, but phi will play a central role. The powers of phi are called ghost number. We will see all this. And picture number. And then there will be these things called picture changing operators. You will see as we go. Okay, so let's keep going though. So we've got T of beta gamma with Z with beta gamma of 0. We just want to do this calculation. So this whole thing is at Z, and then we've got beta gamma at 0. Now let's calculate. Okay, what I'm going to do is to keep the maximum singularity in this thing. So first question, what is the power of the maximum singularity? Z to the power? Not quite. 1 over z cube. Because beta with gamma gives 1 over z, gamma with beta gives 1 over z, and there's one derivative.
Oh, each term has one term.
Yeah. You thought it was two derivatives, right?
Yes.
Okay, excellent. So all we have to do is to do the contractions and take the derivatives. Okay, so let's do the first term. First term is beta with gamma was minus 1 by z. And then we have del z of that. So that's plus 1 by z squared. So 1 by z squared. Gamma with beta was 1 by z. So 1 by z cube. Do you agree? This term with this term gives 1 by z cube. Okay. So into 1 plus, now there's minus lambda. And then let's just compute this. Gamma with beta was 1 by z. Beta with gamma was minus 1 by z. Del by del z, or del z of minus 1 by z squared.
So you have basically two sort of checks, you will get the linear return for phi from this computation.
Yes.
One parameter is determined.
Yes.
And then dimension of beta will fetch the linear return for zeta eta.
Yes.
And then you need to check for gamma, dimension works out or not.
Gamma is what?
Beta gamma is into the phi times eta.
Okay, yes, both. That's one check. That's one check.
And then you should see the
Central charge, that would be another check. Yeah, so that the dimensions work out consistently is one check, and that central charge works out is another check. Yeah. Okay. So let's look at this. So that's plus, and then minus 1 by z cube with a 2, right? 1 minus 2 lambda. 1 minus 2 lambda prime. Now, why does he call it lambda prime? I suppose lambda prime is what he uses for, I think he's calling, he wants, let's use Polchinski's notation. For him, this is lambda prime, okay? I suppose he'll reserve lambda for the BC part of it. Okay, so that's 1 minus 2 lambda prime. Great. Great. Now, what about how do we reproduce this? Now, our phi's were just standardly normalized bosons because phi was minus log z. Okay, and remember that our stress tensor was del phi was what was it? Minus 1 by alpha prime del x del x? Does somebody remember? Minus 1 by alpha prime del x del x? So that's minus 1 by 2. So our stress tensor was minus half del phi, and then possibly a linear deltron piece. So plus something we don't know, a times del square phi. Okay, and beta gamma, this at z, and then beta gamma was del phi at 0. Now from the canonical term, this minus half del phi, are we going to get a 1 by z cube? From this term in the OP, will we get a 1 by z cube? One contraction, so we never get identity. So we're not going to get a 1 by z cube. Right? We'll get a 1 by z square with a del phi. So, but with this term, we will get a 1 by z cube. Okay, so let's work out where we get from this term.
Yeah. That's basically the term which is close to primary of, because del phi would be a primary without the
Exactly. Well said. So, so Upmanyu's comment was, why did we not get a 1 by z cube here? It was because del phi was a primary of the standard free boson theory. And a primary of the standard free boson theory has 1 by del squared, 1 by z squared times operator times dimension. That's the maximum singularity. If you get a 1 by z cube, it was not a primary. Okay? But now we've changed the stress tensor, so the rules have changed. Del phi may or may not be a primary. It's not a primary. Okay? It's not a primary, and we see that from the fact that the OPE has a 1 by z cube. Let's calculate the 1 by z cube. Okay, so to calculate the 1 by z cube, it's A times del z squared of minus 1 by z, plus 1 by z. There's one minus because there was a minus in the OPE.
Yeah.
And there's one minus because we took a derivative from the other side.
Yeah.
Okay, now this will get 2 minuses in the derivatives, so we'll get 2 into 3, so that's 6a by z cube.
Oh, not 6, I think.
2.
Yeah.
2,
Just
says 2, sorry, 2a,
over.
2a over z cube. Thank you. And therefore we conclude that our stress tensor, so 2a must match 1 minus 2 lambda prime. And so this a here had to be plus 1 minus 2 lambda prime by 2. Okay, let's check if we got that right. Yes, 1 minus 2 lambda prime by 2 this is our final answer for the stress tensor. Is this clear? Okay, any questions, anyone? Okay, good. That's what we use for BC system. And what about, were there some i's in the BC system?
Yes, I del square h.
I del squared h times 1 minus 2 lambda by 2. Okay, very good. So basically, you know, the BC system, that makes perfect sense. Because as far as the current is concerned,
This is arbitrary lambda prime.
what? A lambda prime was a lambda prime of the beta gamma system.
The lambda prime, only what was the non-trivial part here?
No.
It is bosonic.
There's nothing I mean, there was no check. It could have worked for any lambda prime. But we fixed the linear dilettante slope.
This I understood. You fix the linear dilettante slope from this computation.
Yes.
Now, when the calculation was done with BC system,
Yes.
that was exactly dual to this phi.
Yes. It was the same calculation, except for some signs. Okay? And for that reason, we got the same thing, except for an extra I.
That I was.
That I is the signs that the BC system is fermionic, beta gamma system is bosonic.
Oh, so that was I.
Yeah. So that the numbers work out right in modulus is very satisfied. The i's are there because of signs. Okay. Remember that there the current operator is I del h. Here it is del phi. So these signs that are okay. Great. Now that we know this, we can now figure out what the weight of e to the power phi is. Okay? Now we've actually worked this out maybe a couple of lectures ago. So if somebody can help, if somebody has it in his, there's no her here. So okay, so somebody has it in his notes and can tell me, please immediately tell me, otherwise I'll work it out again. When you have a linear dilettante system with a term here, what is the weight of e to the power alpha phi? We worked this out. Go on. Well, somebody who has it with factors. So e to the power ikx has alpha prime k squared by 4 plus ia alpha prime k by 2, and a was what?
A was, I think, slope.
Slope.
A was this, yeah, we just left
Yeah.
it. Yeah, A was this.
Plus
Yeah,
a del square
plus
phi?
A del square x.
A del square x. Okay, excellent. So we worked out that the dimension of e to the power I k phi
Yeah.
was k squared over 2
Plus
plus
I A
I A K.
Where A is this 1 minus 2 lambda prime over.
Exactly. Where I is the slope, and therefore is 1 minus 2 lambda prime by 2 I A K. Now we are interested in k is equal to minus I in order to match this gamma. Okay, first let's do k is equal to I. So let's take two cases. Let's keep this on the board. Let's keep this final answer on the board. So k is equal to I will give us k is equal to I will give us minus phi, so that's what's relevant for beta. So that tells us dimension of e to the power minus phi is equal to, we want k is equal to I, so this becomes minus, and I is minus half, so minus half minus 1 minus 2 lambda prime, I was, by 2, which is equal to the minus half
Minus 1.
lambda, minus half, yes, lambda prime minus 1. Okay, let us also calculate the dimension of e to the power phi. This stays the same, that's minus half, but this switches sign. Okay, so in this, so it will be plus minus. Are we getting the wrong answer?
First of all, we should have 1 minus lambda for the gamma, and then beta for lambda prime for the beta.
Well, we don't know what the dimensions of these guys are.
There is plus left.
What? Plus lambda, sorry. You're right, plus lambda prime.
Minus.
Yeah, minus lambda. Okay, great. So, let me check if Pulchinski. Lambda prime minus 1 and minus lambda prime. What do you know? Okay. Pulchinski as corrected by Luboš Mottl. Okay. Yeah. Okay. So that's good. That's good. Now, the weight of beta should have been lambda prime. So that means del zeta should have weight 1. Which means zeta should have weight 0. We're not scared of such things, right? We're brave people. Okay. And the weight of gamma should have been 1 minus lambda prime. Which means gamma should have, sorry, zeta. Eta should have weight minus 1.
Plus 1, right?
Plus 1, sure, right? Plus 1, sorry. Plus 1 minus lambda prime. You're right. Now we're going to see if this fits. So that's the same thing as saying weight of zeta is equal to 0. Okay. Now we.
Standard BC system.
I mean, zeta eta will be one of us from the OP dimension.
Well, let's see. So the standard BC system, one of them has weight lambda, and the other one has weight 1 minus lambda.
Yeah.
Okay. So if we choose lambda to be 0, and lambda to be 0, then we get this zeta is identified with b. The zeta is like b, and the eta is like c. Yeah.
Standard.
Otherwise, lambda has to be 1.
Okay, but now what Pulchinski wants is a lambda equals 1.
Yeah, lambda equals 1 would
Also work.
Yeah.
Polchinski wants lambda equals 1.
Yeah, so 1 minus lambda would be identified with.
So lambda goes to this. Okay, so let's try lambda. I suppose this the central charge thing. Oh, let's see. So we want lambda equals 1. So
So B goes like eta.
yeah. So B goes B. So eta is like B, and
Center term will fix it.
zeta is like yes, exactly.
Like C.
Is like C. Okay, and lambda is 1. Okay, we'll write that down here.
Center term will no one fix it. I'm sorry.
There's a degeneracy.
Sorry. Because it's 2 lambda prime minus 1 plus this. Oh, this was different. Oh, yeah. I don't know the center of
We'll find out. May or may not fix. Maybe there's a choice.
This one will just fix. I don't know the right one.
Let's just write down our final answers. Beta was equal to e to the power minus phi del zeta, and gamma was equal to e to the power phi eta, and we had the stress tensor was minus half del phi the whole thing squared plus 1 minus 2 lambda prime by 2 del squared phi. I'm going to encourage somebody to write these formulas down in a big box so that the next time we need them we can look them up. Okay. Delta of e to the power phi was equal to minus lambda prime. Delta of e to the power minus phi was equal to lambda prime minus 1, and then we have eta is like B dimension and zeta is like C. Lambda is equal to 1, dimension eta is equal to 1, and dimension zeta is equal to 0. Okay, so this gives complete information about our bosonization. Okay, now let's look up the formula Indranil was interested in. That is the formula for the central charge of the BC system. It probably depends on the same combination. It does. It's on 2 lambda minus 1. So I think there may just have been a choice. Yeah. Right. So the formula for the central charge was C is equal to minus 3 into 2 lambda minus 1 whole thing square plus 1. So if we set lambda is equal to 1,
Then you get 1 square lambda is 0, you get minus 1 square.
exactly,
So
it's a degeneracy, and both choices give us minus 3
minus
plus 1, so minus 2. So C is equal to minus 2 from here.
So what I just missed.
Yeah, lambda is symmetrical with half here.
This was the C from the BC system.
Yes, this is C of a BC system.
So now
Okay.
our choice for lambda we sort of decided on.
We decided on would have, as Indranil pointed out, would have made no difference. We had, I think we could have done either. I'm just going to follow Polchinski so we don't keep getting messed up. But we decided lambda is equal to 1. We could have decided lambda is equal to 0. Both choices would have given us the same central charge.
Yeah.
Okay, and so C of eta gamma or eta zeta is equal to minus 2. Okay. Now we also need a formula for the C of this. Do you mind looking up your notes? C is of course equal to 1. That's the ordinary free boson.
Was 1 plus
Plus
12 a squared.
12. Okay. So that's 3 into okay, and then this minus 2 makes this minus 1 plus 3. Okay, so the sum of the central charges of these two theories is equal to the central charge of the original beta gamma system. Okay.
Can you just make the last argument again? I know what this central charge is of the. I know what that central charge is. Then we have this one over here in terms of lambda prime. We haven't chosen the lambda prime yet.
We haven't chosen a lambda prime yet, but the central charge of the free boson theory with this linear dilaton was this much. Okay, we calculated in the previous class. Upan, you looked it up from his notes. We got this. So now we've got two decoupled field theories.
So I have the phi theory has this as a central charge. I have the other theory which has that as a central charge.
Add them up.
Okay.
Okay, so that's this plus this. That changes the 1 to a minus 1. And that exactly matches this formula. Okay? Fine. Now,
How it became 3?
how do, because 12 by 4.
Sorry, that was minus 2 plus this.
Well, yeah, that was minus 2. And this 3 was, Upmanu's formula had a 12. And then there was a 4. Okay, there are other things one could check, okay. One could try to construct this stress tensor in terms of the bosonized language. You take the expression for beta, write del beta, take del beta gamma normal order, just construct that stress tensor, and you should land up on this stress tensor plus the stress tensor of the BC system. Let's write down the stress tensor of the BC system. Just
Behind you, just write B instead of beta.
and there's no signs, right? Let me just check that. Del BC minus lambda b. Exactly. Exactly. So the stress tensor of this guy was with a lambda. So del BC minus 1 del of BC. Now, that which is the same thing, and because del of BC, the del BC cancels, so that's minus B del C. Okay, so in this case, B was what?
Eta.
B was eta. So the stress tensor should be minus eta del T is equal to minus eta del zeta. Okay, and okay, so I'll just leave that as an exercise. Try this. Take these expressions, construct the stress tensor by writing on normal ordered fields. Okay, and check that you recover the expression which is this plus this. No, it should work without a total derivative. The total derivative contributes to a central charge. Del square phi is a total derivative. It's
If you choose other law, like lambda equal to 0,
uh-huh.
then you would have done what? Did you integrate?
Yeah, then we just swap.
You should swap B and C, right? Eta and zeta.
I think you would have got the same stress tensor. Let's check that. So suppose we had done lambda equals 0, then we would have got by Yankee's theorem We would have got del beta, but beta would have been C. Sorry, B would have been B would have been zeta, del zeta, and C would have been eta, and that's exactly minus eta del zeta. Okay, so no ambiguity. Okay, so good. So now we are completely happy with our, whatever you want to call it, enlargification of the beta gamma algebra. Okay, now you see already that we can make many more operators than we could have made just directly with beta and gamma, because beta and gamma have e to the phi and e to the power minus phi. So with beta and gamma you can make e to the power m phi, e to the power minus m phi very easily, but you can't make e to the power square root 2 phi. But with phi you can make whatever you want. See, well, you've got an algebra. If you wanted to make the operator beta, you have to have put del eta with it. But in the algebra, del phi by 2, I mean e to the power phi by 2, it's an element of the algebra.
In an algebra which has many more.
Exactly. So we've got a huge algebra to play with, in which the obvious algebra of operators of the beta gamma system was some small subalgebra. We've got a much bigger algebra that may or may not be useful.
I was going to say, to take our lessons from last time, just because you can expand your algebra doesn't mean everything is physically meaningful.
No, it doesn't mean everything is physically meaningful. The algebra is just a calculational device. Now, it may be that we want to calculate correlation functions of certain elements in the algebra. And the fact that we've got a free field representation of it will help us do it very easily. Now, that's all that we're doing. Okay? And we will want to, okay? We will want to, because the vertex operators corresponding to the beta gamma ground state. In fact, let's work that out immediately. I was planning to do something else, but I think it's a good idea to do this because it will make the point clear. Okay, great. Great. So let us suppose, okay, let's remember now, we did this all for arbitrary lambda prime, but of course for our system lambda prime was 3 by 2. The weight of beta was 3 by 2, the weight of gamma was half. Minus half. Okay, so now, so our expansion, so we're now going to concentrate on the case of interest to us. Okay? So our expansion was beta of z was equal to sum over m beta m divided by z to the power 3 by 2 plus m, and gamma of z is equal to sum over m, okay, gamma of m divided by z to the power minus half plus m. Yes, we need to have that conversation. Let's do that now. Okay. Okay. These m's were the molding on the cylinder. Okay. Now, beta and gamma were the ghost partners of the fermionic part of the algebra, right? So gamma was like an infinitesimal fermionic diffeomorphism, and beta was an infinitesimal, it was a small change in the spin 3/2 field that could not be reached by fermionic diffeomorphisms. Okay?
Your BC system, for BC system, they were conjugate to normal stress tensors.
Normal stress tensor.
And then for stress tensor, you want periodic identification.
Yes. So for BC system, BC will always be periodic.
So that forced BC to
BC to be periodic.
periodic.
But now we are going to sometimes work with all fermions periodic and sometimes work with all fermions antiperiodic. Actually, why all fermions have to be either periodic or antiperiodic together, we will see once we look at the BRST current.
Does that break Lorentz invariance if you don't do that?
If you don't do that, if you don't do that for the physical fermions, yes. But you might wonder, could it be that for the beta gammas? Okay, but you will see that the BRST current has products of beta with fermions, and we will need that the BRST current operator is completely periodic, so that the BRST charge is well defined. Okay, that will force us to map, to tie the boundary conditions of beta gamma with those of the world sheet fermions. We will describe this in the next 2 lectures in detail. Okay, for now just take it that it's going to work, that the boundary conditions of beta and gamma will have to be those of the world sheet fermions. As Indranil pointed out, if we want Lorentz invariance, all the world sheet fermions have to have the same boundary conditions. And we will demand to start with that we have world sheet in. You will, yeah. Lorentz invariance will demand it also other things, modular, it will not be easy to. Anyway, at the moment we will just use Lorentz invariance. All the fermions will go one way or the other, at least to start with, and then beta gamma will be tied to these fermions. So now we've got 2 options. We've got the NS sector, M half integer. Remember, NS sector was antiperiodic on the cylinder, and M is a cylinder label. Or we've got the Ramond sector, where M is an integer.
But as you wrote over here, this is things on the plane, right?
What?
This over here.
This is on the plane. So when we're in the NS sector, things are periodic on the plane, as usual. When we're in the Ramond sector, things are antiperiodic on the plane. Okay, it's just like for the ordinary fermions. Okay? Now, the first question we're going to ask is, how does the state operator map work for the beta gamma system? This is a question we have not addressed till now purposely, because it's sort of weird, okay? And you'll see. So let's see how the state operator map works for the beta gamma system. It works so beautifully for the BC system, right? You'll see how this goes. Okay, so the first question we're going to ask is, what is the state dual to identity? Okay, so state dual to identity, well, let's figure it out. Let's see what we get by acting with beta m on this. Beta m on this is equal to integral of, now same old, z to the power m plus half beta of z. So suppose m, remember m is a half integer. So suppose m is half or larger. Okay? Sorry, minus half or larger. So for m greater than or equal to minus half, this is equal to 0. Right? What about gamma m on identity? This is equal to z to the power m minus half.
Minus 3, unless that.
I wanted m minus half I'm getting, because I want a 1 by z down there.
So is that supposed to be z? It's whatever the power is, subtract another 1, right? And then you have minus a half here, so.
Did I mess up? Maybe. Let me think. You're right. You're right. You're right. You're right. You're right. M plus half. Plus 3 by plus minus 3 halves, please. Minus 3 halves. Thank you. Thank you. Minus 3 halves. Yes. You're right. Gamma of z. And that is equal to 0. Now when is that equal to 0? When m is 3 halves or larger. Identity is Neveu-Schwarz sector. That's good. That's good, but it's a strange state in the Neveu-Schwarz sector.
There are two possibilities.
What?
One is e to the phi times eta, or it's zeta.
Wait. Possibilities for what?
Identity operator.
Well, identity operator is the identity operator. We want to know what state in the Hilbert space it is. Yeah. Look, why is it weird? So what have we concluded? We've concluded that beta of minus, so beta of half, beta 3 halves on identity is equal to 0. That's good. But we also have something that's odd. Beta of minus half on identity is equal to 0. We've also concluded,
Why is that odd?
let me tell you, just give one second. We've also concluded that gamma of 3 halves, gamma of 5 halves on identity is equal to 0. That's good. But gamma of half on identity is not equal to 0. This is okay, but this is funny. Why is it funny? You see, we had something very similar in the BC system, if you remember.
Well, that came from anti-symmetrization.
Exactly. What we had in the, you see, what this is an creation operator. Now, if a fermionic creation operator annihilates the state, it just, sorry. It just means that there is one photon in that state. Because you cannot create 2 photons when you're fermionic. Just means that it's an occupied state. How can a bosonic creation operator annihilate a state? Doesn't work, right? Let's look at the harmonic oscillator. In the harmonic oscillator, if we want a dagger on psi equals 0, all of you know that when you demand A on psi is equal to 0, you get the ground state, which is equal to e to the power minus x squared. A sign changes, and so if A dagger on psi is equal to 0, the state is e to the power x squared.
Sorry,
It's not a state. It's not normalizable.
Coherence states were
A psi equals 0.
Yeah, those were e to the power alpha A dagger.
Yes.
Those are coherent states. This is much worse. This is Schrodinger picture. Those were eigenstates of A, not A dagger.
That was for A.
A. Okay? This
Found to be non-normalizable.
This is not normalizable, and in fact, let's remember that the Hamiltonian of the harmonic oscillator is A dagger plus half.
If A dagger psi is some number times psi, that is not normalizable.
No, it's A dagger and plus half.
Sorry, thank you. A dagger A, thank you, that was a bad one. A dagger A plus half. And now, let us remember also that A dagger is equal to 1.
Yes.
Which means this you can write as minus half plus A dagger. Now, if the state A dagger annihilates the state, the energy of the state is
Negative.
minus half. But there is no state in the Hilbert space with energy minus half. The ground state has energy half.
So
So this is a very strange state.
This might be very stupid, so just add a constant.
What?
So add a constant.
No. But in the normalization in which the vacuum has energy 1, this has 1 unit of energy lower than the vacuum, which is of course because it's not a state in the Hilbert space.
In any state which has the following property, A dagger psi is gamma times psi.
Yes.
Any state has this property is not normalizable.
Yes, correct. Correct.
One of them.
This is one of them. So you see, that's why this is such a funny thing.
Is this a normalizability issue?
Yes.
I understand. So I'm understanding why this is weird, right? Because I have something that doesn't satisfy the Pauli exclusion principle, and then I still have a creation somehow sending me to 0.
Yes.
I understand. So how is this now a statement about normalizability?
So let's work in Schrodinger representation.
Yeah.
A dagger.
I'm sorry to interrupt, but just to get this clear in my head, there's no exclusion principle because beta gamma are bosonic operators.
Yeah.
That's what he was saying. He was saying, despite there not being an exclusion principle,
Yeah.
an annihilation operator, creation operator annihilates the state.
Yeah.
Now let's look at it. So because each of these modes is that of a bosonic harmonic oscillator. So look at it with undergraduate, a single harmonic oscillator. Look at the state which is annihilated by A dagger. Write it down in Schrodinger picture. Write down its wave function. A dagger on state is equal to 0 is a first order differential operator, which you can solve. When you solve it, you will find the wave function e to the power x square. Just one sign changes between A and A dagger. Okay, what was e to the power minus x square becomes e to the power x square. That is not a state in the Hilbert space. It grows too fast at infinity. If you allow such things, you will allow arbitrarily negative states in quantum field theory. Okay? Okay? This is not really a state in the Hilbert space. I want to emphasize that despite this, we're going to use this formalism. Okay? It's plenty weird, okay? Why don't we worry about it? Well, we don't. I don't know. It's a weird thing. This state here, identity, from the point of view of the beta gamma system, is not a state in the Hilbert space. The state corresponding identity is not in the Fock space. We don't want to deal with that state at all. The states that we're going to look at scattering in string theory will never be identity in the beta gamma system. Maybe then some manipulation will make it identity. But in logic, we want to scatter a state in the Hilbert space. Okay? In particular, we will be maximally interested in the ground state. Do you remember that in our formula for scattering amplitudes for the ordinary bosonic string, the unintegrated vertex operators came with a factor of c. Why did it come with a factor of c? Well, it came because of some path integral manipulation. But if you think of it conceptually, it's because c was the operator that took us to the ground state. Do you remember c was dual to the ground state of the BC system? The operator dual to the ground state. So we put the operators in the ground state of the ghosts and scattered. Right? We were scattering the matter excitations. And then, of course, anything that was BRST equivalent to that was fine. Is this clear?
C kind of came because of counting of 0.
That is how it came from a path integral manipulation. But now if you think of it as something, you've got this picture. Strings are coming in. It's telling you what state we are scattering. So what state was it? Well, it was a state that was a 1-1 primary in matter sector and ground state of the ghosts. Very satisfying, right? It was forced on us. It was forced on us, but it's a very satisfying picture. We didn't want to excite the ghosts. Of course, then we can if we want by adding some BRST trivial excitations. It won't make a difference. But the thing we actually wanted to scatter was just in the ground state of the ghosts. Okay? So, we will be for similar reasons, we will be particularly interested in the ground state of the beta gamma system.
So which is not identity.
Which is not identity. It's part of the Fock space. Okay? Please go on.
Yeah, so I was sorry, maybe it's stupid, but this implies that there's no tachyon in the spectrum. I mean, because the identity would correspond to a
Well, not clear yet.
Okay.
Because there may be a tachyon because something that is identity in the matter sector may anyway be tachyonic. It's not yet clear, right? Because we'll have to add up the dimensions of all operators. Okay, and in fact, there is one way of thinking that makes it clear that unless you do something else, there will be a tachyon. That is, just go to light cone gauge. In light cone gauge, there we saw there was a tachyon. If you remember, we did the central, the 1 plus 2 plus 3 analog, and we found there were tachyons in the NS sector. And we will see the same problem, despite all the sophistication, because that's a physical thing, can't go away. Okay, so we'll get rid of the tachyon, but not by this. Okay, more questions?
NS sector has the identity element.
Yes.
And in NS sector, the ground state was identity for the matter. I'm talking about
Yes.
matter part.
Yes.
So in the transformation from the plane to the cylinder,
Yes.
you get a minus C by 24, and you get minus precisely because you get a tachyon.
Yes, you get a tachyon, and actually we check that directly also in by doing the 1 plus 2 plus 3 kind of calculation.
So as long as you are not getting rid of NS sector,
Exactly.
the matter part already got
As long as you're not getting rid of the identity part of the NS sector
that's all. That unless you get
in the matter sector.
in the matter sector.
None of this ghost stuff can really matter, because we went to light cone gauge, there were no ghosts. You know, and there we already saw the problem.
So that is already stays
It's still here with us.
unless we get rid of it.
Yeah, we're going to have to deal with that. In fact, the next class, I thought this class, but next class we'll be dealing with that. Okay? But for now, let's just get the mechanics of the ghosts right. Just conformal field theory of the ghosts right. Okay, excellent. So we're all good, except we have to figure out what is the vertex operator for the ground state of the beta gamma system. Okay. So now what algebra should the ground state of the beta gamma system obey? This guy should not annihilate the vacuum, but this guy should annihilate the vacuum. Right? So what did we have here? What we want is some operator here. Okay, so now what I want, so this you all have in your notes, and I'm going to change this. I want something so that this minus half will become plus half, and this 3 by 2 will also become half. Okay? How will that work? That will work if I had an additional 1 by z here
1 by 0 was the first one.
and an additional z here. Okay? Can anyone think of something that will give us 1 by z here and z there? B was e to the power minus 5, right? Yeah, beta was. Do you remember e to the power minus 5 with e to the power minus 5 was 1 by z? That was one of the first things we did in the lecture. But e to the power minus 5 with e to the power plus 5 was z. Okay, so now suppose we've got this at 0. Now we will get an additional 1 by z. Okay? So now this will become m minus half, and for m greater than or equal to half it will work. This will become m minus half, and for m greater than or equal to half it will work.
Is the statement that the state dual to the identity is not in the Hilbert space?
What? Yes. The state dual to identity is not in the Hilbert space. We will never deal with that state. Unless as a mathematical trick later on, you know, because, but conceptually we'll never deal with that state. Okay? This state is perfectly in the Hilbert space, so it's the vacuum. Okay? And it's the state dual to the operator e to the power minus 5. Is this clear? Let me check that. Yeah, he's got the same thing, e to the power minus 5. Okay? Let us quickly work out the dimension of this state. The dimension of e to the power minus phi was lambda prime minus 1. Lambda prime was 3 by 2. So e to the power, this state, the dimension of e to the power minus phi, let us remember, was equal to half. He says e to the power L phi has dimension minus half L squared minus L, and L is equal to minus 1. Yeah, half. Good. Okay. We are almost done for today's lecture. Let's quickly finish off the lecture by looking at the Ramon sector. Okay. Once again, what we're going to do.
Is there any way of remembering this? If you have any intuition or anything, what is the number?
The e to the power minus phi. Well, it's very similar to the C. Yes, C was the operator dual to the vacuum, the BC system.
Yes.
And C was e to the power with the plus or minus. It's like that, right? Bosonized C was e to the power minus phi. Okay. And from this, you might be able to guess what is the operator dual to the Ramon sector vacuum. It's like e to the power IH was psi, and the Ramon sector was e to the power IH by 2. So you'll get something like that also for the Ramon sector. Let's check. Yeah. Now in the Ramon sector, again we have 0 modes.
On the cylinder, you don't have anything.
What?
Even in the Ramon sector, if you are on the cylinder.
In the Ramon sector, on the cylinder, we have m equals 0.
You have m equal to 0. So therefore, both of them are coming with fractional powers.
Both of them are coming with fractional powers on the plane. But we had states which
In Ramon sector, you will still have 0 mode.
You still have 0
There has
modes.
to be some half. There is no other choice because then you need 2 of them at least.
Right, exactly. So now we're going to have some options. But let's go. Okay. I mean, we have to decide what to do with the 0 mode sector. But apart from that, it will be very clear. Right? So,
Since you have 0 modes, you have more than one vacuum.
actually, you're going to get an infinite number of vacua from the 0 mode sector because it's bosons. Right?
Because it is boson, so there is no square.
This is like, it's the action is like PDQ. Okay. So it's a very strange system, okay? It's a very strange system, this beta gamma system.
Then I am taking
Okay, let's work it out without worrying about the 0 modes, and then we come back to the 0 modes. At the moment, let's just do some algebra. Now, this expansion, of course, continues to work. I'm doing this bad thing of rubbing out things. I know this is what the first they tell professors, that you must never rub out, write it again. But okay, just to speed it up. Right? Okay. What do we want? What do we want from okay, first let me just do this. Let me ask, what do I get when I get e to the power, I had e to the power minus 5. Let me just see what I get when I get e to the power minus 5 by 2. Okay, this would be a natural guess. It will give us one of the choices, and then we'll have to worry about the 0 modes. It's a question of whether beta 0 mode annihilates the state or gamma 0 mode annihilates the state. One of the two will, and we're going to make the choice that will be like, if you remember, we had B annihilating the state.
So for this you will not have the periodic identification. For example, when you bosonize psi into the IH,
Yes.
then we had an I new H, that when you consider different ground states of fermion in bosonized vector, it was e to the minus I nu minus half times H.
Yes.
And then there was an identification of nu going to nu plus 1.
Yes.
This will not be here. Only then you will probably have infinite number.
Nu goes to nu plus 1 in sectors, not in states. You know, nu goes to nu plus 1 is adding an extra psi operator.
Yes.
It's just that it doesn't give you a new sector. If you remember, what we did was to divide up the Hilbert space into sectors labeled by nu,
Yes.
where that nu range from 0 to 1.
Yes.
Okay? Here you will still have e to the power alpha phi, where alpha ranges from 0 to 1. You see, our sectors are just sectors of chiral algebra, such that within a sector you can get from any state to any other state by acting with beta and gamma themselves. So we will still break up into sectors of chiral algebra, but this is not identifying states. Okay? So within a sector we may have two different states that we may want to look at. That's a separate question. Okay, so let's quickly just do this algebra and then we can break for today. Suppose I look at e to the power minus phi, so e to the power minus phi by 2, e to the power minus phi by 2. Now let's work this out. Okay, this is z to the power m, it gets rid of the plus half. Okay, and this here gives you z to the power m minus 1. Okay, and so this is equal to 0 for m greater than equal to 0, and this is equal to 0 for m greater than equal to 1. This, if you think about, is exactly the analog of this choice we made in the bosonic sector. If you remember, there was this funny thing there, that we had two states in the BC system.
And which one to call ground state?
Which one to call ground state? And in fact, we looked at, you know, if you remember when we looked at what was physical Hilbert space, we demanded that a physical Hilbert space be that part of Hilbert space that is annihilated by the B operator, by B0. No, we demanded this. We actually found, if you remember, there were two copies of physical Hilbert space. And then we argued that one of them, never appeared. It gave rise to these non-analytic contributions to S matrix. Yes, delta functions. They could only appear in some very odd way. Okay, so there was some argument that it's the part that was annihilated by B0, which was the physical Hilbert space. Okay, this would be the natural analog. It's annihilated by beta 0, and in fact it's a natural analog in the sector which maintains supersymmetry. And so if you really want to maintain supersymmetry, it's not just natural, the supersymmetry will force this on you.
This is the sector, which sector is this?
This sector is the Ramon sector. On the cylinder, Ramon sector is periodic fermions.
Cylinder it is periodic.
Okay, so this is the sector in which the whole theory is supersymmetric on the world sheet, if the fermions and bosons have the same boundary conditions and obey all the same conditions. Now clearly the supersymmetric version of B0 annihilates the vacuum, is beta 0 annihilates the vacuum. So this is one motivation for this choice. Now we'll come back, we'll see what we can say more about this choice. This is going to be our identification of the operator dual to the Ramon sector. Okay, and what is the dimension of e to the power minus phi? Well, the general formula is minus L square by 2 minus L for e to the power L phi. Let's check that that works. That's for L equals 1, L equals minus 1, that's minus half, plus 1, so that gives the half there. Okay, for L equals phi, that's minus 3 by 2. That also works. Okay. Now, here we have L equals minus half. So that's minus 1 by 8 plus half. Plus half. So that's half minus 1 by 8. So that's 4 by 8 minus 1 by 8. So that's 3 by 8. Delta of e to the power minus 5 by 2 is equal to 3 by 8. You know, whoever's noting down all these things, please note down so we can we can appeal to you in future class. H is equal to 3 by 8. Sounds lovely. Okay, excellent. So we've computed the scaling dimension, we computed the operator and the scaling dimension of the state dual to the Raman state vacuum and the NS vacuum in the for the superconformal ghost. Okay, so we've completed the first round of technicalities now. The first round of technicalities with the system is now done. Okay, in the next class, which we'll have on Tuesday, we will now start seriously setting up the superstring. All the elements we have in question, we have under control. There are 2-3 things that we still need to do. The first and most pressing thing is to understand how we get rid of the tachyon, if that's possible. And then we have to more seriously set up the rules for string scale. We have to look at the BRST current, we have to look at the physical state conditions, and we have to more seriously set up the rules for computing scattering amplitudes. Okay? So in the next class we'll start by looking at truncations we can make. So we've got this matter sector, we've got the ghosts, and what we're going to do is mod out the theory by a symmetry. Okay? We're going to mod out the theory by symmetry. Symmetry is minus 1 to the f left. But we will see, we'll do this systematically. We'll mod out this theory by some sort of symmetry, okay, and find all possible consistent truncations of this general structure. And we will find some of them are supersymmetric. Some of them are good, some of them remove the tachyon, some of them don't. The ones that don't, we'll be less interested in, the ones that do, we'll be interested. Okay, so we'll systematically analyze possible consistent truncations of the sector of the structures we built. The structures we built are quite, it may seem complicated because you've not seen this before, but it's quite simple. It's all free theories.
It gets worse.
It's like that book. Have anyone read this book called The Castle by Kafka? There's a guy who's trying to enter a castle and he's trying to persuade the doorman. And then the doorman says, look, what's the point? I may let you in, but there's a much bigger doorman behind me. This guy never gets past the first doorman through the book. Okay.
Is that 3/2 or 3/8?
3/8. Where? The dimension of this is 3/8. Yeah, that's right. That's 3/8.
Okay.
Plus 3/8. Because this was minus half. Yeah. Okay. So, the structure is quite simple because we've got just free theories. We've got free bosons, we've got free fermions, and then we've got ghosts. The BC system is now our old friend. In addition, we've got this beta gamma system. Beta gamma system is a bit weird. I take your point, but we've written it in terms of things that are less weird. There's the linear dilaton scalar, and there's an eta zeta system, all under control, right? All under control. Now we will have to understand how to take this structure and use it.